All right, we're going to talk now about some examples of integration. Before we move on with doing the examples, I have to mention some of the basic rules of uh, integration. One of these rules comes directly from the fact that, as I mentioned at the end of the first part of this lecture, that the derivative is the integral is the opposite operation of the derivative. So if you were given something like find the integral of f prime of x dx, then that's just gonna be equal to f of x plus c. Because you're looking for the antiderivative. You're looking for a function whose derivative is this. So you take the integral of the derivative, you get back the function, the original function. Now, if you have, for example, the following, let's say little f, the integral of little f of x dx, let's say that's equal to some antiderivative f of x, capital F of x plus c, then if you took the derivative, if you take the derivative of an integral f of x, you get back f of x, you get back the integrand, because these two operations, the derivative and the integral, cancel each other out. To put it in very simple terms, let's say you have 2 plus 5 minus 2. There's a plus 2, there's a minus 2, they cancel out. You know that the answer here is 5. Okay, even if you were to add first, 2 plus 5 is 7, minus 2 is 5. Or if you subtract first, you do 5 minus 3 is 2, 5 minus 2 is 3, plus 2 is 5. So either way you do it, you get 5. And in reality, the 2's are just canceling each other out. That is the case with the antiderivative, and we will see examples of this throughout. Now, I am going to write a theorem which will give us our first rule of integration. It's probably one of the most basic rules and one of the rules that gets used the most. Once you get really good at this, you will never forget it. That I will tell you. You kind of never forget this particular rule. And it's called the power rule for indefinite integration. So, theorem. If you're given an integral, say x to the p dx, right? If somebody asks you to find the antiderivative of a polynomial or a monomial x to the p, then that is going to be equal to x to the p plus 1 divided by p plus 1 plus c, where p is not equal to negative 1, it's a real number, and c is an arbitrary constant. I will not be proving this, but we will be using this theorem throughout. So let's do an example. Let's say we were asked to describe the antiderivative of 3x. Okay, so we're looking for a function whose derivative is 3x. Well, how do we go about getting a solution? The first thing you do is write 3x inside of the integral sign, because we are going to find an antiderivative, and whenever we're trying to find an antiderivative, we write the integral symbol to let everybody know that that's what we're doing. As soon as you see an integration sign, you know that you're looking for an antiderivative, and whoever comes to read your paper should be able to see it. Now, what is the first thing that we do? Well, the first thing that we do is notice that we're looking for the derivative of x. Okay, remember the dx tells us the variable of integration, so we're looking for the derivative of x. Remember when we had the power rule? The power rule said that if you had something like this, like c, let's say c times x, and you're looking for the derivative of this, right? you're looking for the derivative of this, then you could take out the c. So you could do c times the derivative of x because you're not worrying about this constant. The same thing is true with the antiderivative. So because I'm only looking for the derivative of c of x, I could pull out this 3 to the outside of the integrand of the integral symbol. So what I really have is 3 times the integral of x dx. This is called the constant multiple rule. It's the same name as for when you take derivatives. Okay. Now, this x is to the power 1. So when we take the derivative, when we find the derivative, the antiderivative of x to the 1, we will be using the power rule. So what does the power rule say? X to the p is the same thing. The antiderivative of x to the p is x to the p plus 1 divided by p plus 1, where p is the power or exponent. So I'm going to do this on the side. I'm going to call this side work. So I have x to the 1, the integral, and by the power rule up there, I'm told that that's x to the 1 plus 1 divided by 1 plus 1. This is the same thing as x to the p plus 1 divided by p plus 1 from up here. So what do I get? Well, 1 plus 1 is 2, so you get x to the 2 divided by 2. So now we know that the antiderivative of x to the first dx, or an antiderivative of, I should say, an antiderivative of x to the first dx is x to the 2 plus x to the 2 over 2. So what do we get? We get 3 times, so now this whole thing becomes x to the 2 over 2 plus c. So we have 3 times x to the 2 over 2 plus c. This is the only time that I'll write the c on the inside of this parentheses, and I'll explain that in a second. So this is equal to, when you multiply through, 3x squared over 2 plus 3c. Now, because the c represents any constant, it is very cumbersome and unnecessary to actually write the 3c. So we actually just write 3x squared over 2 plus c. We don't bother with this multiplication of the c. So whenever you do whenever you find an antiderivative, you just ignore the c and you just add it at the end. You just add plus c at the end. This is something that becomes, you see a lot of memes actually of this online when students are first learning how to do this, because they always forget to add the plus c. If you don't have the plus c, your answer is incorrect. Let me just be clear about that, because this is the general antiderivative. You know, that c could be any number. C could be any number, so you have to add it. So let's say if somebody gave you, again, let's do another quick example. Somebody gave you 2x to the 2dx. Using the same techniques that I did above, I'll take the 2 out, and I have x squared dx. So that is equal to 2 times, now I will find the derivative of x squared dx. So let me do it on the side, x squared dx. And by the power rule, that is x to the 2 plus 1 divided by 2 plus 1, because it's x to the p plus 1 divided by p plus 1. So I get that this antiderivative of x squared dx is equal to x cubed divided by 3. Notice that now what I'm going to do is I'm going to write 2 times x cubed divided by 3 plus c. I'm going to put the plus c on the outside instead of the inside. And now I just multiply, so I get that the solution of this is 2x cubed over 3 plus c. How can you make sure that your answer is correct? How do you check your solution? So let's check. To check our answer, we simply take the derivative. So to check our answer, we'll take the derivative with respect to x of 2x cubed over 3 plus c. Well, what is the derivative of, and you know, we could use our different rules that we had, so we could separate this work on them as derivative of 2x cubed over 3 plus the derivative of constant. We know that the derivative of a constant is 0, so this is just going to be 0 up here, back here. And now by the power rule, we have 6 x to the 2 over 3, because 2 times 3 is 6, and then you minus 1. But now 6 divided by 3 is 2, so we get 2x squared plus 0, which is 2x squared. But notice that that's exactly what we began with, 2x squared. That's what we wanted to, that's what the integrand we had. So our solution is correct. We found the antiderivative for 2x squared. So every time you want to check that your solution is correct, you simply take the derivative, and you should be getting back whatever is on the integrand. Okay. Let me do another example. Let me do one more example. I mean, this whole section is going to be examples now. So let's say somebody asks you to find the integral, the integral of 1 over x cubed dx. Okay. So we want to know what this is equal to. Well, here we have a situation where this does not look like the only rule that we have. The only rule that we have is the power rule, that is x to the p dx is equal to x to the p plus 1 divided by p plus 1. But this is not of that form, because this particular one is of the form of 1 over x to the p. So what I will do is first rewrite it so that it looks like this. So we rewrite it so that we get x to the negative 3 dx by the rules of exponents. And now this definitely looks like our rule. And then we can apply the theorem. So the theorem says that this is going to be equal to x to the p, well, p in this case is negative 3, plus 1 divided by p, which again is negative 3 plus 1. Well, that is equal to what? That is, I forgot the plus c here. That is equal to negative 3 plus 1 is negative 2, so this is x to the minus 2 divided by minus 2 plus c. You could write, if you want, you could bring down now the x to the denominator because you have a negative exponent, so this is going to be negative 1 over 2 times x to the minus 2 plus c. That will be your solution. You could keep the negative sign in the denominator for the 2. I like to put it in the middle. Not minus 2 up here, plus power is positive here. But you could keep it in the middle, you could keep it in the denominator, it's perfectly fine. But I like to write it in the middle. Okay, let's do another one. Another example. What if somebody asks you to find the antiderivative of the square root of x dx? Well, again, this is not of the form of x to the p, so we write it in that form. I'm going to keep writing the rule so you remember it. You should do that as well. It helps you remember it. So again, the first thing we do is rewrite it. The square root of x is the same thing as x to the 1/2 power dx. And now this is of the form x to the p. Well, this is x to the p. P here is 1/2 plus 1 divided by 1/2 plus 1. Now 1/2 plus 1 is the same thing as 1/2 plus 2 over 2. Remember, to have fractions, you need the same denominator. So it's the same thing as 1/2 plus 2 over 2, which is the same thing as 3 over 2. So we have in the exponent, we have x to the 3/2, and in the denominator, we have 3 over 2. But we don't want to leave this as a complex fraction. So what we'll do is multiply with the reciprocal of 3 over 2. So we will actually have as our solution 2x to the 3 over 2 over 3. If you didn't see how that happened, this is x to the 3 over 2 divided by 3 over 2. And then if you use the keep, change, flip method, you keep the first one the same, change the sign to multiplication, and flip the fraction, and then you multiply across. So this is 2 times x to the 3/2. This is just 2 times x to the 3/2, and 1 times 3 is 3. So we get this is our solution, and don't forget the plus c, because the plus c is part of our solution. Okay, so that takes care of, the square root function. What if you're given a trigonometric function, like the following? What if you're riding on the bus and somebody comes up to you and gives you the antiderivative of 2 sine of x dx? Well, this one is gonna be a little bit more challenging because we don't have a rule for it. I didn't write any rules for it, but we do have a couple of rules that we know from before. Namely, we know that the derivative of sine of x is equal to cosine of x, and we know that the derivative of cosine of x is equal to negative sine of x. Now, I always recommend students to write in this way, even before an exam. Like if we were on campus, I will ask you to always, in the first piece of paper, write everything that you know before I even give you the exam. And if you're taking a calculus class, this is probably the first thing that I will write, because it's easy to forget them. It's easy to forget when the pressure kicks in of an exam, it's easy to forget what the derivative of sine and cosine are. Same thing for the derivative of tangent. It's also useful to write it. The derivative of tangent is secant square x. So it's always useful to write it. Now, why do we write them? Because remember that the antiderivative is just what came before it. So what is the antiderivative of cosine of x? Sine of x. What is the antiderivative of negative sine of x? Cosine of x. What is the antiderivative of secant square x? Tangent of x. So now we have a few things that we can work with. Well, first of all, let's go back to our problem. I have the integral of 2 times sine of x. Again, because the 2 is being multiplied to sine, then by the constant multiple rule, I could pull it out. So I really have the integral of sine of x dx times 2. Now, what is the antiderivative of sine of x? Well, these are the derivatives. These are the solutions, right? So if I look at on the right side, these are what the derivatives are equal to. So that means that the left side is the antiderivatives. Now notice that there's only one sign here, and that's a negative sign. I have a positive sign here. So I have to do something about it. I need to make this negative sign into a positive sign. So what I really have is cosine of x, the derivative of cosine of x, is negative sine of x. Right? I'm just not gonna write the x. So if you divide both sides by -1, we get that the derivative of negative cosine of x is equal to sine of x. That we know from before. The derivative of negative cosine is sine. But now this is an antiderivative for sine of x, because when you take the derivative of negative cosine of x, you get sine of x. We're working backwards. So now we have that the antiderivative of sine of x dx is negative cosine of x. So we multiply by negative cosine of x, and again remember to add the plus c, so we get that the antiderivative of 2 sine of x is negative 2 cosine of x plus c. And again, check your solution. You could check it. Take the derivative, d dx of negative 2 cosine of x plus c. That is equal to d dx of negative 2 cosine of x plus d dx of c. Well, this is equal to, by the constant multiple rule, minus 2 times d dx of cosine of x plus 0, because the derivative of constant is 0. But now the derivative of cosine, we got up here. That's negative sine. We did that here. The derivative of cosine is negative sine. So we have negative 2 times negative sine of x, which is equal to 2 sine of x, which is exactly what we had in the integrand when we began, 2 sine of x dx. So this is in fact the antiderivative. Negative 2 cosine of x plus c is the antiderivative of 2 sine of x dx. Okay, so let's do one more of the These are the very general examples that show the basic rules that we had prior. So let's say we are looking for the antiderivative of 3 over x dx. Okay, now when you look for this antiderivative, you gotta be a little bit more careful. So first of all, let's use the constant multiple rule. Let's take out the 3, because the 3 is not a variable. So by constant multiple rule, I could pull it out. So I have 1 over x dx. Now, for this antiderivative, I am not going to rewrite it. So I'm not going to do x to the minus 1 dx. The reason why I'm not going to do that is because this doesn't actually work. If you try to use the theorem that I gave you earlier, the theorem says that p is not equal to -1, so we cannot use it. And if we try to use it, this is what will happen. We have -1 plus 1 divided by -1 plus 1. Notice that it's going to be x to the 0 divided by 0. We cannot divide by 0. So the theorem doesn't work for this case. The theorem actually doesn't work at all. But we do know, if you remember from way back in the day, earlier in the term, we actually do have an antiderivative for this. Because, if you recall, the derivative of ln of x is equal to 1 over x. So we have an antiderivative for it. ln of x is the antiderivative. So what we get is 3 times ln of x plus c, which is simply 3 ln of x plus c. So knowing this antiderivatives and these derivatives from before goes a long way. Definitely goes a long way. Let's do one more, just because it may come up in the third part of this lecture when we do more interesting examples. The antiderivative of e to the x dx. The antiderivative of e to the x dx is just e to the x plus c, because if you remember, the derivative of e to the x is simply e to the x. Okay, so if somebody gives you, well, hey, comrade, what's the derivative of e to the x? You used to say it's just e to the x. So now you say, what is the antiderivative of e to the x? It's just e to the x. If somebody gave you, 3e to the x dx, well, you take out the 3, and then now you have e to the x dx, and we just found out that the antiderivative of e to the x dx is e to the x plus c. So this is equal to 3 times e to the x plus c, which is just 3e to the x plus c. And that makes sense, because when you take the derivative of this, you get 3e to the x, and the c goes away because it's a constant. In the next part of this lecture, we're going to look at a little bit more challenging examples, more interesting examples, and some techniques that you will use to evaluate integrals, indefinite integrals.